Okay, we're going to do another example of matrix inversion, and one of the reasons to throw this in, we've done an example before, but I wanted to show another example. One of the reasons to throw this in at this point is we have now discussed some definitions by what is meant by the rank of a matrix. So it's a good time to discuss matrix inversion. So in this section, we're only going to consider square matrices. And basically, the inverse of an n by n matrix is denoted by a to the minus 1, and it's also an n by n matrix. And the definition is that if you take a times a to the minus 1 or a to the minus 1 times a, you'll get I, the identity matrix. And if you remember the identity matrix, it's also referred to as a unit matrix. It'll have dimensions n by n, and it'll have ones along the diagonal and zeros everywhere else. And notice that if you have an inverse, the order of multiplication doesn't matter, which is somewhat unique. So the order of multiplication doesn't matter. You'll still get the inverse matrix whether you multiply a times a minus 1 or a minus 1 times a. Now, if a has an inverse, then we refer to a as a non-singular matrix. If a does not have an inverse, we refer to a as a singular matrix. Also note that if we do have an inverse to a, that inverse is unique. So the existence of the inverse exists if and only if the rank of a is equal to n. And so we haven't discussed determinants yet, but that's also true if and only if the determinant is not equal to 0. So a is non-singular if the rank of a is equal to n, and it's singular if the rank of a is less than n. So the easiest way to find the inverse is to use Gauss-Jordan elimination. Now, we discussed Gaussian elimination. What does the Jordan part mean? The Jordan part means we're going to continue doing row operations until we get the unity matrix. So determine the inverse of this matrix. So here's our matrix A. So the first step is to augment the matrix with the identity matrix. So here's our ones in the diagonal. And now what we're going to do is we're going to do row operations until the matrix on the left side is converted to the identity matrix. So I won't go through all of these, but you can see the operations that are being done, starting with the two bottom rows, then continuing until we have an upper triangular matrix. And notice that we're doing the same row operations on our unit matrix, or on our identity matrix, so it's now changing. Okay, continuing now, we now have our upper triangular matrix, and so now what we're going to do is we're going to do row operations on the top two rows to eliminate these two terms and this 3.5 term here. So we'll continue with the row operations, and you can step back through these to be sure you understand how they occurred. But basically how we want to finish is we want this matrix on the left to be the identity matrix. If we do that, then the matrix on the right, it turns out to be, is the inverse of our original matrix A. So this is the identity matrix, this is A minus 1. In fact, that's what this says, and you can check that by multiplying these two matrices together. If you multiply these two matrices together, you should get the identity matrix. So that's just an example of how to take the inverse of a matrix using Gauss-Jordan elimination.